Thanks to everyone who's made it this evening. The session will be recorded for those unable to make it due to timing or conflicts. Today, Noah's going to give his second statistical seminar, and the focus is on an introduction to causal inference, which is building upon his last seminar, which was on the basics of estimation and things like that. Thanks, Noah.
Thank you, Luke, and thank you all to thank you to those who are here today. Appreciate you coming. I'm just going to share my screen, and then we'll get started. So just give me a second to get that set up. Okay. Sorry, just give me a second. Okay. Hello, everyone. Thank you so much for being here. As I said, today I am going to give you a brief presentation on causal inference for biomedical research. This is the second in our statistical seminars for CARA 2024. Last time we talked about how to estimate population quantities of interest, or QOIs, from a sample, how to quantify uncertainty around that estimate, and how to test hypotheses about that quantity of interest using the estimate. We didn't spend a lot of time talking about what quantities of interest we are actually going to be estimating, but that is more of the focus of today's talk. We briefly mentioned about how causality is straightforward in a randomized control trial, which is often abbreviated as RCT. But when we don't have a randomized control trial, we need to do some additional work. And the focus of today's talk will be on understanding what work we need to do to establish causality when we can't run a randomized trial. This is not going to be, well, there's going to be some notation in this. I prefer not to have too much technical notation in a conceptual talk, but it really does help kind of solidify some ideas. Last seminar, we used this notation, which is written or read as the expectation of y given x, and it is represented as this E, which stands for expectation, and then in brackets we have y, and this bar means given, and then x is our conditioning set or conditioning variable. And the way we can understand this is as the average of y. For example, for a binary variable, we can understand the average to be like the proportion of events within a subgroup defined by x. So for example, for people who are 65 years old or older, that could be the conditioning variable, or people who receive the treatment. So we'll use this notation fairly frequently in this talk. So I just wanted to remind you of it. Causality is central to biomedical research, and that's why we're talking about it today. It's critical for understanding, causal pathways within biological systems, which we use to develop drugs. So, how molecules and our systems interact together to create responses in our bodies. It's used to understand the effects of medical practices or interventions on patient outcomes. It's used to understand the causal effects of noxious exposures like smoking or lead or air pollution on people's health, which is critical for implementing health policy. Broadly, we're going to understand causal inference in the context of the effect of some treatment. I'm going to use the word treatment, but you can understand that to mean policy or intervention or exposure on an outcome, and that outcome can be whatever it is. For example, like the probability of survival after a few months, could be medical expenses, could be time to death, this framework is broad, so it's just about these kind of somewhat abstract relationships between treatments and outcomes rather than uh, like only being allowed to work for certain treatments or outcomes, which is why causal inference is kind of this universal branch of statistics that has utility across all social and biomedical sciences. So there are a few requirements to be able to make a causal inference, which is to say to establish that one thing causes another. First, we need temporal precedence, which is to say that the treatment occurs before the outcome. We need association, which is to say that the treatment is associated with the outcome, which is, I have a little asterisk here because there are some odd cases where you can understand causality without necessarily an association, but those are like a little bit niche. And then the kind of critical requirement is that there's no alternative explanation. So there's no kind of hidden third variable or a selection effect that explains why two variables are associated. We'll talk more about like how that can arise, but I think a classic example is this idea of this association between like ice cream sales and murder rates, which is a kind of classic causal inference mistake example. They seem to be associated, but it's kind of clear that there is an alternative explanation, which is to say there's not, it's not the case that buying ice cream causes murders. It's the case that there's this other thing, which is heat, that causes people both to buy ice cream and to commit murders somehow. To make a causal inference in an applied science, we need to have a well-defined treatment and outcome. So we need to identify, for example, the distinction between treatment assignment and treatment receipt. So if we're interested in the effect of a drug, is it the effect of being prescribed the drug or the effect of taking the drug? And those are both different treatments that have an important distinction in their kind of causal force, their efficacy, and the things that relate to those treatments and the outcomes that they have. Understanding the effects of obesity, how can we disentangle that from the effects of the causes of obesity, like diet and activity? Understanding the effect of being a race, being from a certain race versus experiencing racism. Those are also kind of fundamentally interlocked in a certain way, and we need to define our treatment when we're trying to understand discrimination and those kinds of effects. And then with respect to outcomes, we need to understand whether we're interested in all-cause mortality after some intervention or death due just to the complication of the intervention. So anyway, these are the kind of conceptual things one needs to think about, but there's also a mathematical formulation of causality, which is kind of the underpinning for all of the like statistical work that we can do to estimate causal effects in the biomedical sciences. And that's what we're going to be talking about basically for the rest of this talk. There is this framework that is used to understand causality called the potential outcomes framework. And I'm going to explain that in the next few slides. So the idea is for a treatment, which I'll label A. I know it's a bit odd to label the treatment A, but that is kind of the way it's done in some literatures. It usually stands for action. And let's say it can take on the values 0, meaning, let's say, no action, and 1, meaning action, or 0, meaning control, and 1, meaning treatment. We have an outcome, Y, and we have an individual, I. We can define these potential outcomes, which are the outcomes that one would have were one to receive the treatment or were one to receive the control. And these are written as Y superscript 1 for the potential outcome under treatment and Y superscript 0 for the potential outcome under control. These are sometimes described as counterfactuals, which is to say they are counter to fact. They are distinct from the observed outcome. They are a kind of hypothetical outcome that would occur under different scenarios of treatment. So before you receive the treatment, there is kind of two paths that you can take. If you receive treatment, you go down one path and one of your potential outcomes is realized. And if you were to receive the control to not be treated, you would take the other path and your other potential outcome would be realized. It is a little bit abstract, but this does provide this like mathematical foundation for causal effect estimation. An important idea is that these potential outcomes exist before the treatment is actually given to you. So again, they're kind of within you, and we can understand treatment as revealing one of them. Why is it so important to reveal one? Well, we can define the individual causal effect, which is to say the causal effect of the treatment on for an individual as the difference between that individual's potential outcomes. So this is, again, this like mathematical definition of a causal effect, and defining it in terms of potential outcomes creates this like very clear definition. Although for a lot of people, including me, earlier in my career, these were very like counterintuitive, because we often think about, the variables that we have in front of us, but potential outcomes are kind of fundamentally unobserved, and I'll talk about that shortly. In addition to this idea of the individual causal effect, there's also the average causal effect, which you can just understand as the average of the individual causal effects. So for each individual, there is the effect of receiving the treatment, which is to say the difference between the potential outcome under treatment and the potential outcome under control. And if you were to take everybody in the population, consider their individual causal effects, and take an average of that, which again, I'm denoting with this E, meaning average or expected value, what we arrive at is the average causal effect. There is this kind of problem that you might have recognized already. The fundamental problem of causal inference is that only one potential outcome is observable for each unit. So here is a kind of hypothetical data set, basically, where we have 4 individuals, 1, 2, 3, and 4, and 2 of them are receiving control and 2 of them are receiving treatment. And we have their observed outcomes, but I have also added columns for their potential outcomes. And for those that received the control, we know their potential outcome under control. It's simply their observed outcome. But we don't know their potential outcome under treatment. We don't know what would have happened had they received the treatment. Similarly, for the people who received the treatment, those with A = 1, their potential outcomes under treatment are observed. They are just the observed outcomes, but their potential outcomes under control are not observed. So how can we estimate or even talk about average causal effects when parts of our definition of those causal effects is fundamentally unobservable? And note that this is not just like, oh, we didn't collect enough data, and if only we could collect enough data, we could have these variables. Like, this is a population issue, that in the population, you can only either observe the potential outcome under treatment or the potential outcome under control for each individual. So how can we talk about or estimate or define causal effects without this? That's what the rest of today's talk will be about. Before I move on, I just want to pause and see if there are any questions, because I know this is kind of like a weird topic.
So just to clarify, Noah, there's different. We're talking about average effects for a population as well as average effects for an individual, which will become important later when you talk about the estimands. But can you just delineate between those two a little bit just to consolidate that?
Sure. So the idea is that there each individual has the effect of the medicine or the drug or the treatment. And if we knew what the causal effect for that individual was, we would know whether treatment works for that individual, which would be amazing. We would kind of solve medicine essentially, because we could know for every patient, should we give them the medicine, what medicine will work best for them. But the kind of fundamental problem of causal inference is that we can only observe one of the potential outcomes. What we're about to talk about, so great transition, Luke, is that despite not being able to observe both potential outcomes for each individual, it is still possible to estimate average causal effects. And that is this kind of like this beautiful kind of miracle of causal inference, is that despite these fundamentally missing potential outcomes, we can still estimate average causal effects over the population. So although we can never know for each individual what their two potential outcomes would have been, we only get one of them, we can still learn from individuals about populations.
No, I
Hopefully
had a
that
question.
made sense. Yes. Yes.
So here you've represented y as like a discrete like binary variable. Can it also be continuous? And like if so, what is the
Absolutely.
interpretation of tau? How can you subtract two discrete variables like when you calculate the tau factor?
Yes, the outcomes and therefore the potential outcomes can be any type of variable. I just decided to use a binary variable because I think they're simpler, but it could be something like hospital cost, which could be the hospital cost if you were to experience one type of surgery, and your hospital cost if you were to receive a different type of surgery. Or it could be time to death or time to readmission, which are kind of not just 0, 1 discrete variables, but potentially continuous. So the nature of y doesn't really or doesn't affect the interpretation of causal effects. For any outcome that you have, you can define potential outcomes on the same scale, essentially, and therefore the individual causal effect for that outcome. Does that make sense? Did I answer your question?
Yeah, sounds good. Thank you.
Okay, thank you. If I misunderstood anything, just please like feel free to correct me and I'll explain again. So don't feel like you need to just accept my answer if it wasn't the answer to your question. Anything else before I move on? Okay, I'll move on. So I kind of hopefully built up a little bit of suspense by saying that despite us not having access to the potential outcomes for any individual, we can still estimate average causal effects. And that is what we are going to do. So under certain assumptions, the expected potential outcome is equal to the observed outcome among the people who actually received the treatment. That's what this kind of expression represents. So this first line is saying that under certain assumptions, which I'll talk about in a second, so don't think this is a universal truth, but under certain assumptions, the expected potential outcome under control is equal to the expected observed outcome among those who received the control. Similarly, the expected potential outcome under treatment can be equal to the average outcome for those who received the treatment. And the reason this is such an incredible possibility is that these quantities on the right are fundamentally, or not fundamentally, they are potentially observable, which is to say it's possible to collect data on them. They are not subject to this like fundamental problem of causal inference, whereby they like can fundamentally not be measured. We can measure them and observe them, and then we can use all of the kind of techniques we talked about in our last seminar to estimate them and quantify our uncertainty about them. So what are these assumptions that give us this incredible power? The first critical assumption is called consistency. What this says is that your observed outcome corresponds, your observed outcome corresponds to the potential outcome. I'm sorry, I'm going to restart that. Your observed outcome is equal to the potential outcome corresponding to the treatment you actually received. This seems like it might just be part of the definition of a potential outcome, but other ways to understand consistency are that there are no unmeasured versions of treatment. So for example, if you receive a drug, there's no like kind of alternate versions of the drug that might actually have different potential outcomes if you were to take them. Like maybe if the generic was different from the name brand in some way, it often isn't. Simply being like assigned to take the drug is not kind of enough to identify the causal effect. Another important like way that consistency could be violated is when there's interference by other units, which is to say that the treatment status of other patients around the patient in question affects their potential outcome. So this is highly relevant in like infectious disease, where like the vaccination status of an individual's surroundings, the people around them, affects the effect of whether they are vaccinated or not. And you can think of this as just like moderation, but another way to think of that is that there is a potential outcome under any possible distribution of treatments in the people around you, and those can be considered different treatments. So consistency says there is none of that going on. The even more critical assumption, which is very hard to meet, is the assumption which is called no confounding. And we represent this symbolically by saying that A, which is to say treatment assignment, is independent of or unrelated to, that's what this kind of upside down T means, the potential outcomes. When I first saw this statement, I was like, how could that be? Because isn't the whole point that treatment affects the potential outcomes? That's what the causal effect is, but it's not. Recall that the potential outcomes exist within an individual before they receive the treatment. That's how we can define causal effects without actually assigning treatment to any individual. So what this is saying is that anything that might affect your potential outcomes doesn't also affect the treatment. So this is a statement about treatment assignment. And it's saying the treatment assignment is unrelated to anything that's related to your potential outcomes. When could this ever possibly happen? Well, when treatment is unrelated to anything, which is to say, when it's randomly assigned. So in a randomized trial, this assumption of no confounding is met if the randomized trial is done successfully. In certain types of trials, consistency is kind of automatically met. And in those scenarios, we can estimate these expected potential outcomes from the observed data. So really kind of amazing thing about randomized trials, and that's why they're so powerful. Unfortunately, though, we often can't run a randomized trial. It may be unethical or impossible, but fortunately, we're not stuck. There are other assumptions that we can use to still estimate our expected potential outcomes from the observed data. And these other assumptions rely on a new variable, x. This is kind of a complicated statement, but what this is saying is that under these additional assumptions, which I'm about to tell you, we can represent the expected potential outcome under control as, we'll first take a look at this like inner expectation. This is the average outcome for those who received control and have a specific patient profile. That's what this X means. So we can estimate the causal effect. We can estimate the average outcome for those who received treatment and have a given patient profile. And if we average that across all of the patient profiles, we can arrive at the expected potential outcome under control. Pretty cool. What are these assumptions? Well, we need consistency again, but now we need a slightly weaker assumption than the assumption of no confounding, and that is that there's no unmeasured confounding. And essentially what this assumption means is there is a set of variables, X, that defines these patient profiles, such that within subgroups of X, for each patient profile, the treatment is unrelated to the potential outcomes. So the treatment is as if randomized for each patient subgroup. It's a bit of an abstract assumption, and I'll talk about how we can find this X and determine whether one exists in a second. We need one final assumption, which is called positivity, which just means that every individual or every patient profile is eligible for either treatment or control. The probability of being treated is between 0 and 1, strictly between them. Okay, I'm going to pause again briefly. Any other questions before I move on to how we figure out what this X is, what these variables are?
So these are incredibly important slides, guys, and are really relevant to what we're doing. Now, if you go back to the first slide, I'll just give it like a real world example.
This one?
Back to the no, back to the no confounding one. So the whole previous page. And then forward.
Sorry.
Yep. So for
this is a slide
consistency,
about.
guys, imagine that there's a study comparing surgery for aortic valve replacement versus a TAVI, like a minimally invasive one, and you're in clinic and you're trying to decide whether your patient should have surgery or a TAVI. You need to know that surgery and TAVIs where the study were done are similar to how it's done in Melbourne. So if that study is using a different device, different types of surgeons, it's not really like for like. Whereas 100 milligrams of aspirin is 100 milligrams of aspirin is 100 milligrams of aspirin. So there are certain exposures or interventions that are not going to be similar across different regions in the world. I think that's pretty important. And then if you go forward one slide, Noah. So the no unmeasured confounding is really important. Imagine you see an observational study of the association of being on ECMO before cardiac surgery and mortality. And the study says that, ECMO was associated with death. And you think, well, hang on, what sort of variables were they adjusting for? And if, let's say they didn't adjust for much, you might say, well, ECMO probably is life-saving in certain patients. And the reason it looked like it was associated with death is because this study didn't adjust for their blood pressure being 30 and them hemorrhaging out of their chest. You know, there are certain variables that studies either can't or don't adjust for.
I have a question.
Great, thank you.
Oh, sorry.
Sorry, I was going to say those are really great examples, Luke. Thank you so much for clarifying. I really love that the surgery example. Yeah, go ahead with your question. Sorry.
Yeah, sure. I was just like wondering about like positivity. So this kind of implies that you're assigning patients to treatments. So like this really only applies to like RCTs, right?
It doesn't. So this idea is that I may be using the word assignment kind of in a looser, abstract way. Patients may be selecting their own treatment, or doctors may be selecting it for them. But the idea is that there are no subgroups for whom kind of like the treatment decision is purely deterministic. It is known with absolute certainty what kind of treatment this patient profile will receive. If there is such a scenario, we simply cannot estimate the causal effect for that person because it's almost like the potential outcome under the other treatment isn't even defined if that type of patient profile cannot receive the treatment. Does that make sense?
Yeah, so you want like a mixture of different treatments in that subgroup, basically, right?
Yes, exactly.
Okay.
So
Thank you.
if there's a patient profile and among that patient profile, you only see people who receive the treatment, you know, that it may be, you may be curious what the causal effect of the treatment is for that patient profile, but it can't be computed fundamentally because they never have the other potential outcome. They never have the control. So yes, positivity is this like requirement to be able to define and then also estimate the causal effect.
Cool. Thanks so much, Noah.
Thank you. Okay, let's talk about how we can find this set of variables. So Luke mentioned, this idea that if you fail to adjust for certain variables or measure them, then the association that you see doesn't necessarily represent a causal effect. There is a kind of yet another formalization of this concept that is represented in what are called DAGs, not dogs, but DAGs. DAG stands for directed acyclic graph, and a DAG is a diagram that represents causal relationships. What is really cool about DAGs is that it is a kind of mathematical formalism in addition to a like graphical tool to understanding causal relationships. And this mathematical formalism has kind of graph theoretical rules associated with it that allow you to determine which variables you need to adjust for to satisfy the assumption of no unmeasured confounding. So on the right is an example of a pretty simple DAG. Here's some like brief notation, but DAGs essentially only have these little few components. An arrow between two variables just means that one variable causes the other. So A with an arrow pointing to Y means A causes Y. A box around a variable means we are kind of imagining the system within subgroups of that variable, or said again, like conditional on that variable. So for example, we might be looking at the association between, taking some drug and death, but only among people who are within an age range, or only within people who have some pre-existing condition. You're looking at an association within a subgroup defined by a variable. That's what it means to kind of put a box around that variable. And then in DAGs, you often and really must have these also unmeasured variables. So a DAG doesn't just represent the variables that you have measured in your data set, but it represents a causal system, which could include variables that you didn't measure. And these unmeasured variables are one of the most important parts of a DAG because they kind of allow you to represent the limitations of your data set with respect to understanding your causal system. So there are some rules that DAGs give us that allow us to understand whether two variables are associated with each other and the nature of that association. That is, whether that association is a causal association or a non-causal association. So the most basic relationship is just if A causes Y, we say that A and Y are going to be associated, and that association is causal. If A causes another intermediate variable X, which also causes Y, then A also causes Y. A would be associated with Y, and that association is causal. And we call X, in this case, a mediator. So for example, if the way a medicine works is by increasing some process in the body, which yields some outcome, that activation of that intermediate process is the mediator. And the medicine still causes the outcome, but it does so through this other variable, the mediator. If some variable X causes A and it also causes Y, you would also expect A and Y to be associated with each other, but that association is non-causal. And in this case, we call X a confounder. So a common cause of two variables is a confounder of those variables. And then finally, when we have two variables that cause a third variable, so when A and Y both cause X, there is not an association between A and Y, unless there is some other association for some other reason. But simply two variables causing a third does not automatically mean that those two variables are associated with each other. And so what we say is the association between A and Y is blocked. I know that seems like a kind of aggressive language, but you can just understand it to mean there is no inherent association just because two variables cause a third. That third variable is called a collider. And maybe you may be wondering, like, why are we even talking about that if it doesn't have a causal relationship? I'll explain in a second. So these are kind of like the basic rules of association from a DAG. So if someone gives you a DAG and says, this is my understanding of these causal relationships among the variables in my system, you can determine whether any two variables are associated with each other and the nature of that association, which is to say whether it's causal or not, based on these rules being applied to the DAG. There are also associations that can emerge when you condition on variables. So if we condition on a mediator, which is to say we look at this association within a subgroup defined by the mediator, then the association between A and Y is blocked. We block the causal association between A and Y. I think a kind of like classic funny example is to say that like there is no association between smoking and death if you only look at patients with lung cancer or emphysema, because those are like, you know, the main ways that smoking causes death. So if you subset your population or your sample just to those people who, based on a mediator, it will seem like there's no relationship between the cause of the mediator and what the mediator causes. But that isn't a true representation of the causal system. So conditioning on a mediator blocks a legitimate causal pathway. Conditioning on a confounder also blocks that association, but it blocks a non-causal path. So it's actually a good thing to adjust or condition on a confounder. And then the reason I brought up colliders at all is because adjusting for a collider actually induces a non-causal association. So there's a kind of classic example of this, which is called Bergson's bias. This old doctor noticed that at his hospital, there was a negative association between like the severity of diabetes and the severity of toe fungus. Why would that be? Well, if you condition on people in a hospital having diabetes, and the more severe it is, and having severe toe fungus will both bring you to a hospital. And so if you look at patients within a hospital, if you condition on being in a hospital, there is this association between these two variables that is induced, that is not reflective of some actual causal relationship between those two variables. So conditioning on colliders is kind of dangerous. Why do we need these rules? Well, we use these rules to identify which variables we need to condition on or adjust for in order to remove all non-causal associations between our variables and prevent us from inducing non-causal associations. Together, this is known as the backdoor criterion. The backdoor criterion is met by a set of variables X that blocks all non-causal associations between A, the treatment, and the outcome Y, leaves open all causal associations between A and Y. So for example, it should not include mediators because mediators do not leave open those causal associations. They block them when conditioned on, and they don't open non-causal associations between A and Y, between the treatment and the outcome. So given our understanding of DAGs, there's like advice that has emerged about how to select X, like how to know what variables we need to adjust for in order to make a causal inference. We need to adjust for variables that cause the treatment, A, and the outcome, Y. We need to ensure no variables that are caused by the treatment or the outcome are part of X, and no variables that are colliders are part of X. So with these rules, we can select this X, this mysterious X that allows us to satisfy the assumption of no unmeasured confounding and thereby estimate the causal effect of our treatment. just from our observed data, even though the causal effect, the average causal effect, is defined in terms of variables that are fundamentally unobservable, the potential outcomes. The way that we do this procedure is step one, we draw a DAG of our system. We scour the literature for all causal relationships among the variables that we're interested in studying. We use algorithms to find an adjustment set that satisfies the backdoor criterion. And then, given that we have found the variables that we need, we then go out and collect those variables and then use those variables to estimate the causal effect. Alternatively, we're not collecting the data ourselves, but we can evaluate whether our data set is sufficient to estimate the causal effect by satisfying backdoor criterion. This is a kind of example of a DAG that I developed based on some literature. I won't go too deep into it, but the idea was to estimate the effect of serum urate, which is some enzyme, you probably understand that better than I do, on cardiovascular disease. And these were all kind of the factors that were identified that might be related to these, which include taking blood pressure medication, obesity, nutrition, sex, ethnicity, your HDL cholesterol level, whether you're taking a statin or not, your propensity to use preventative medicine. From this, it's not like obviously clear what variables you need to adjust for, but there are algorithms that can be used to select those variables in a valid way. Okay, we're going to talk now about estimation. This won't be that long. I know this is kind of like the fun part and probably the part that Luke is most excited for you to learn about, but I really wanted you to understand like the kind of fundamentals of causal inference before we got to like the more estimation-y parts. We'll talk more about...
just very, very quickly, do we have to go to the literature, or can we use our clinical knowledge to pick a series of measurable confounders?
That's a great question. Absolutely use your clinical knowledge. The literature is important for kind of demonstrating to readers that you have selected a sufficient set of variables, but the literature cannot cover everything, and there are lots of things that it's obvious that these two variables are related to each other based on your clinical knowledge or experience, or what you've seen in the room, and you should know to whether these variables need to be adjusted for, or what the causal relationship is between them. The literature can be useful when you need to justify your DAG to readers, or if you don't know whether these variables are related to each other. So, someone might say, I think your DAG is like a little too extreme. You're assuming these causal relationships are all over the place. You can say, well, actually, like this study did find that these variables are causally related to each other. So I wanted to like include that in my DAG and make sure that my DAG is like as liberally generated as possible, so that I can most accurately generate the variables that I need to adjust for. Sorry, I had intended to take a pause, but I was looking at the clock, and so I wanted to make sure that I don't keep you too long. So I'm just rushing through again. Any other questions before I move on with estimation? Okay. So now that we know the X that we need to adjust for, we can represent our expected potential outcomes, which are these kind of fundamentally unobservable quantities, as potentially estimable population quantities from observed data. These on the right correspond to these quantities of interest that we were talking about in the last seminar, these kind of potentially estimable quantities from actual data. So the causal inference is what links these two together, and the rest, estimating this thing on the right, is statistics. It's not causal inference anymore. So let's talk statistics. There are a few methods that we can use to estimate these quantities on the right. Some examples are matching, weighting, regression, or G-computation, and doubly robust methods. If you haven't heard of any of these before, that's totally fine. These are advanced statistical methods. We're just going to talk about matching and weighting briefly today, and next seminar, we will give an example of performing matching and weighting, and you in your analysis will just be doing matching and weighting, so you don't need to worry about the others. Essentially what matching and weighting do is they adjust the sample to remove the associations between X, this like set of variables we've identified, and the treatment. So in doing so, they kind of modify the DAG to simulate a DAG under a randomized experiment where nothing causes the treatment. A critical concept in understanding matching and weighting is imbalance. Imbalance is the degree to which the distribution of a variable differs between treatment groups. So for example, here is a kind of mirrored histogram. On the x-axis is our variable x, which takes on values from, let's say, 0 to 25. The white histogram on the top gives the proportion of control units with each value of x. So for a value of about 5, we have that approximately a quarter of the people of the control units have that value. And on the bottom half of this histogram is the distribution of this variable for the treated units, so the proportion of people who are treated with each of these values. Imbalance is the degree to which these two distributions differ from each other. We can see that for high levels of X, only treated units are present. And that in general, the distribution of X is kind of to the right for the treated units from the control. When groups are balanced on a variable, which is to say they're not imbalanced, then this, which is the mean of the variable in that group, is unbiased for the potential outcome, the expected potential outcome. Where does imbalance come from? Imbalance is caused by this treatment selection based on these variables. So if a variable affects whether you receive treatment, there will be imbalance on that variable between the treatment groups. In a randomized control trial where nothing affects treatment because it's purely randomized, there is no imbalance in large samples. In small samples, like sometimes random things can happen, but overall, the distribution of every variable will be the same between the treated and control in a randomized trial. So in matching and weighting, the goal is to remove imbalance to mimic a randomized trial by making the distribution of every variable in X the same between the two groups. For matching, the way we do this is we find untreated units that are close to treated units or similar to treated units, and then discard the rest. And so what we're left with is just a sample of treated units and control units that are very similar to each other. And we can estimate our treatment effect tau as the mean of the outcome in the treatment group minus the mean of the outcome in the control group among those who are remaining in the matched sample. So it's kind of like we're carving a randomized trial from our observational study. There are many ways to customize matching. For example, like how closeness or similarity is defined, what algorithm is used to match, how many units are matched, how far is considered too far to be allowed to match, whether we're allowed to reuse units and match them to more than one. The most popular, but also worst method is called one-to-one propensity score matching without replacement. I won't go into detail about what that is because I'll give you some resources on it later, but you'll see this method used a lot in medical research, despite it having like famously bad performance. And it's just for cultural reasons. There's no good reason. It's because people don't understand how to do anything better, but I will teach you. For weighting, it's very similar to matching. Instead of kind of selecting a piece of our sample that is balanced, we compute weights represented with W for each unit that balance the variables. The idea is that in the weighted sample, the distribution of a variable will be the same between the treated and control groups. And the way this typically works is that units that resemble the other group are upweighted, so they're given more importance in the analysis, and individuals that don't resemble the other group are downweighted. And what you're left with is a weighted sample that looks like it came from a randomized trial. The way we can estimate our treatment effect is by computing the weighted means in each treatment group. This is just a fancy way of saying weighted mean. There are many ways to estimate weights. Some optimize balance, some focus on precision, some focus on simplicity, speed, or the ability to do valid inference on them. The most popular and also worst method, which is often the case, is called inverse probability weighting. It's actually not that popular in medical research, but it is more in epidemiological research. It's bad just because it's basic. There are much better methods. Again, I'll show you how to do those later. There are some considerations when you perform a matching or weighting analysis. First, you need to assess balance, which is to say you need to assess the degree to which the matching or weighting procedure actually yielded balance in your sample. So do the distributions of every variable look similar between the treatment and control group after doing the matching and weighting? There are numerical and graphical approaches, and it's important to demonstrate not just to you, the analyst, that the adjustment was successful, but to the reader also to prove to them, hey, yes, you can make a causal inference from my study because the matching or weighting was successful at imitating a randomized trial by creating balance between the groups. We can assess the precision of a matched or weighted sample. So when you do matching, you are throwing away data. The people who were not matched are just gone from your sample. That is obviously going to decrease your sample size, which affects your precision. And there's a kind of analog to that with weighting as well. When you estimate weights, you also decrease your precision in a way that's similar to throwing out data. And then you need to assess generalizability, which is like, to what extent does your sample represent the target population that you are trying to generalize your inference to? Luke briefly mentioned this. I didn't focus on it too much, but there's this idea that you can estimate treatment effects for different types of individuals, including the individuals who are likely to receive treatment, or the individuals who are likely to receive control, or the entire population, or some subset of it. And when you perform matching or weighting, it's possible for the sample that you're left with to not resemble this population that you want to generalize your inference to. So for example, maybe the matching restricts your sample only to people who are very young, but you want to make an inference about the average effect across all ages. So in that sense, matching was not successful at ensuring generalizability. Some final steps, once you've done the matching or weighting, is the important part, estimating the treatment effect. We can often do this by just running a regression of the outcome on the treatment in the matched or weighted sample. Again, it's a little technical and statistical, so if this doesn't mean anything to you, it's okay. We'll go more into it later. We need to quantify our uncertainty, which we talked about in the last seminar, by, for example, computing a confidence interval or a p-value for a hypothesis test. And then we also have this ability to assess the sensitivity to unmeasured confounding. So we think we measured all of our confounders, but what if we didn't? We can actually assess how our inference might change for a given hypothetical confounder that we didn't measure, and how strong a confounder would need to be in order to change our inference, the direction of the effect. These are all important parts of running the analysis. But once we've done this, we have our causal effect estimate, which we can write up in our paper and say, hey, we estimated a causal effect. We adjusted for the set of confounders, which we identified by using our clinical knowledge to develop a DAG. And here is the uncertainty around our estimate. And that's estimating causal effects. So that's all I have today. Next session is November 3rd, and we will be doing an interactive walkthrough, working with some CARA data, and Luke and I will be co-leading that. As always, please feel free to reach out to me on the CARA Slack if you have any questions. I'm going to include a tutorial for propensity score matching and weighting that I wrote for Harvard, which you are welcome to access, and I think it would be really useful for you to read it, especially if you felt a little lost during this presentation, which is completely reasonable. In our last few minutes, I'm happy to answer any questions and stay on a little past the time, but thank you very much.
Thanks, Noah. That's absolutely amazing. If I could just ask one thing.
Mhm.
So the reason we're doing matching and weighting is because it's not a randomized control trial, right? Like we're just trying to simulate what that would have been in a retrospective study. Is that right?
Yes, that's exactly right. So if we had a randomized control trial, we wouldn't need to do matching or weighting because our samples would already be balanced, which is to say there would be no association between any variables and our treatment, and we would meet the assumption of no confounding, which allows us to simply estimate the average causal effect as the difference in means using this estimator or this kind of this equality. When we can't meet this assumption, because, for example, we are using retrospective data, as you mentioned, instead we have to appeal to this other assumption, which relies on the set of variables x, and then we have to appropriately adjust for x by using matching or weighting in order to estimate these quantities.
Thanks, Sashi. Are any other question?
Yes, thank you, Noah. It's really good. Can you explain a little bit more about how matching when you discard data will reduce the effective sample size? Because I thought we normally have the sample size calculated for each group, and then when you match, either you double 2:1, 1:1 ratio, you should still reach the same sample size. So how does it reduce your sample size with matching?
Sure. So, let's say you have 100 treated units and you have 500 control units. So you have a total of 600 units in your sample. These are patients in your database. If you were to perform one-to-one matching, what that would mean is for every treated unit, you would find one control unit and match it to them. So at all 100 treated units receive a match, which is one control unit each. So you match 100 control units to 100 treated units. That is your new sample. Just those 200 units is your new sample. Everyone else that was not matched is literally thrown away in the sense that they are not used for the rest of the analysis. They are not used to estimate the causal effect. And so by discarding those 400 individuals from your sample, you are reducing your precision just as you would if you had started with a smaller sample.
Right. So you won't match it to reach the original sample size. If you calculate sample size, you need 200 per group. You won't get 200 with treatment and then 200 with the matching. You reduce
right.
it.
So yeah, the whole purpose of matching is to get rid of individuals from your sample. So the intention of matching is to discard individuals. It's those individuals that do not contribute to the causal effect because they're so unlike other individuals in the other treatment group. So you are kind of starting with a big sample and kind of trying to find a little narrow window that is like a randomized trial from your sample, but that window is necessarily smaller than your original sample.
Thanks.
Yeah, we've actually had journal reviewers before criticize matching studies we've done for not being able to find a match for 100% of patients who received an intervention. So for an example, pulmonary artery catheters, we had a matching rate of 70%, but the journal reviewer said, well, the 30% who didn't get a match, that's where the action is going to be, and you weren't able to have any insights on that. So one of the metrics of success is matching rate. There's lots of ways we'll be evaluating this. Everything today is really high yield for your individual projects for CARA. The session will be recorded. Noah's available on Slack for questions. We're going to do a walkthrough where we're all going to be actually uploading data into RStudio and conducting some matching analyses on the data we'll be using at the event. And so that will hopefully, for those of you who didn't catch everything today, like me, you'll be able to do it. Like you'll be able to consolidate things with a walkthrough, a bit of practical. Any other questions before we let Noah go?
Yeah, I do have another question, if that's okay. Because I'm trying to get my head around the weighting. So obviously if you weight one sample above the others, you're not just changing the one kind of confounder you're weighting them for. You're changing all of the other confounders. So I guess I wonder how you actually end up weighting so that all the confounders are kind of matched across your two groups.
It's a great question, and it is kind of incredible how it does it. It's hard to describe except that it works, which is that you can kind of tell an algorithm I want you to estimate a set of weights that balances all of my covariates, all of my variables. I want them to look the same between my treated and control groups. And kind of the magic of modern computers is it can do it. It can just find those weights that do that. So there are, sorry if I'm being a little abstract and not really answering your question, except to say like it's possible, but that is kind of the answer. And I think that when we have a look at some real data during our next session, or if you want to take a look at the tutorial yourself and run the code yourself, you'll just kind of see this like miracle that is the weights doing their job at balancing the variables. It is really an incredible thing. So this idea that like, individuals that resemble the other group are upweighted is like a heuristic to help understand like what's going on with weighting, but the actual method is, computational and statistical and a little bit abstract.
So is it kind of like a gradient descent thing where like just like converges to like
it can be, but that's not like a general way that weights are estimated. There are many different ways, and some of them are these like optimization methods. Gradient descent is, a way of optimizing, but it's not the only way, and it's not the way that the kind of best performing weights are estimated. So yes, there is this idea generally that you can use optimization to kind of find this ultimate set of weights that does the best job. And I'm excited for you to test it out and see how they work.
Cool. And how well does it do? Like, is it always going to outperform matching in terms of like the like weightedness of both groups?
It's a great question. It's kind of hard to describe how to choose between matching and weighting. One way to think about matching is it's the same as weighting, except everybody can either receive a weight of 0 or 1, whereas weighting in general allows you to receive a weight that could be any positive number. So in that sense, like weighting is more general and more flexible, and it's more amenable to these optimization algorithms that operate on like continuous weights. So weights are definitely more flexible in that sense, but there are some advantages to matching that obviously I didn't have time to go into today that allow you to incorporate substantive information in a more useful way. The kind of matching is often more interpretable to audiences because it's less abstract and statistical than weighting. When you do matching, you just arrive at 2 samples and you can kind of understand these samples the way you would understand a randomized trial. Whereas with weighting, like the way the weights are incorporated into the rest of the analysis can be confusing to non-technical audiences. So there are advantages like, science communication advantages to matching. There are some statistical advantages in some cases, but it's, I could talk about this forever because this is literally what I study, but it's, a bit nuanced of a discussion. I'm happy to send you articles if you're genuinely curious about how to choose between them, but really it's like whatever makes most sense to you and your audience, and whichever one allows you to achieve balance while maintaining precision in the optimal way.
Okay, cool.
Sorry if that was a bit unsatisfying.
No, that was really interesting. Yeah, really excited for the next session as well. Thank you.
Noah, thank you so much. That was awesome. Guys, the recording is available through Teams. Noah's going to send around the tutorial and some documentation. And we'll get to get hands-on the next session, which we're really excited for. So thanks very much, everyone.
Thank you. Bye, everyone.
Bye.